Good morning, everyone. A lot of people have showed up, so thank you for that. And welcome to tips and tricks using xSignals and pin link tuning in high-speed design. Let me quickly introduce myself. My name is Gert Friepenberg. I work as a hardware specialist at Stoneridge Orlaco. We're actually a tier 1 automotive supplier, and we design and manufacture automotive cameras for on-road trucks. And the idea is that in a few years of time, all the mirrors from the trucks are going to be replaced by cameras. So I've been working on that for the last 5 years. Why this talk? Well, in my field, in my company, in the last 5 years, when I started working at the company, the average board we did was 4 to 6 layers. Nowadays, when we do a board, it's 8 to 18 layers. So that has progressed quite rapidly, actually. And also, gigahertz nowadays is the new normal. We started doing 8 megahertz bandwidth PAL cameras, and now we're doing MIPI, DDR, SerDes signals, PCI Express, etc. And of course, when I talk about gigahertz, it's not per se the clock speed of the signal, but it's rise times. I think you've heard that a lot of times these past few days. Also, in my work, everything has to be first time right. So first prototype, when it arrives, you can do a day of design verification, then they're gonna catch it, get it off your desk and ship it to the customer for some demonstrations, some marketing or whatever. And usually what also happens is that the planning of the project is so sharp that you don't get any time to do any major redesign. So if you don't have it first time right, you're basically screwed. And also, well, I think most of the people here have managers above them, so probably a lot of them have this experience. They all say, please finish the design in the same amount of time. So 5 years ago, I got, let's say, 6 weeks to finish a board. Today, the board has become 5 or 10 times as complex. I still get the same amount of time to finish it. So yeah. So actually, what is a high-speed PCB? So who is this talk? Well, I found a quite nice quote actually. And to put it simply, high-speed PCB design is any design where the integrity of your signals starts to be affected by the physical characteristics of your circuit board, like your layout, packaging, layer stack, interconnections, etc. So if you start designing boards and you run into troubles like delays, attenuation, crosstalks, reflections, or emissions, congratulations, you're in the world of high-speed PCB design. So probably almost everyone in this room fits that category. So basically there are, I think, 3 challenges in high-speed design. The first one is timing. So that means, are all the signals on your PCB layout actually arriving at the proper time in relation to other signals? So most high-speed signals are driven from a clock. And when the clock arrives at its destination, you have to make sure that all the signals arrive in time just before or just after that same clock. Second one is actually integrity. So you send out a signal from point A to point B, and do the signals actually at the destination look the way they're supposed to? I mean, there's also always going to be some change in the signal, but if you have too much change, you're gonna ruin your signal integrity. The third one is actually noise. So that your signal along the way from point A to point B encounter any interference along the journey, and do they get into trouble from that? Because we all know every PCB generates some kind of noise, but is it enough to, or is it less enough to pass emission standards, and do we not corrupt our data? To these 3 challenges, there are actually 3 solutions. First one is proper impedance. So having proper impedance between the transmitter and the receiver will impact the quality and the integrity of the signal. Second one is length matching. So like we said, all high-speed signals are usually related to a clock, and signals have to align before or after, but within a certain time window at their destination. And the third one is conductor spacing. So the closer conductors are relative to one each other, the more they're going to influence each other, etc. In this talk, we're going to primarily talk about timing and length matching. So we're going to ignore the other parts a bit. I took a DDR3 layout as an example here. Why DDR3? Well, it could be DDR4 as well, but in my experience, DDR layouts, they have a really nice, they are a combination of where all the aspects of high-speed design come together. So you got a lot of timing constraints, but you got also have to take care of impedances, signal integrity. There's limited board space. You can't have enough crosstalk, etc. So a design like this brings everything together, so to say. Well, this design actually exists of two physical chips. We got an SoC on the left, and we got two physical DDR devices. Well, if we simplify it a bit, we have on the bottom here, there are 4 data groups. Those are more or less point-to-point connections to each specific DDR device. And on the top, there are some address command and control and some clock signals. And they are going from the SoC over to the first DRAM device, and then in what we call a flyby configuration over to the second DRAM device. And if you would have more DRAM devices, over to them, etc. And at the end, they're terminated with some resistors. So on the physical PCB, it actually looked like this. We got, as you can see on the left, there's a 10-layer stack up. And we got actually on the bottom, this is just for thermal reasons for this design, so don't bother about why the chips are on the bottom. But so we got the SoC there, and we got the same 2 DRAM devices over here. On the top, there is some bulk capacitance, some decoupling capacitors, some miscellaneous stuff, and some termination resistors, which are not that important for this talk. So as you can see, there are 4 high-speed signal layers. The first signal layers have the 2 first data bytes actually routed from the SoC over to their respectable DRAM devices. So that's more or less point-to-point routing from A to B. And there are some address command and control signals there as well. Second signal layer has some clocks in the bottom, or at least at the center. And there are some address command and control signals there as well. Well, there is wrong button. Third signal layer, same story. Some clocks in the top and some address and command and control signals going to the DRAM devices. And finally, the last signal layer has some more point-to-point data bit routing, and it has some command and control signals going from DRAM device 1 to DRAM device 2. So as you all perhaps noticed, I've gone a bit crazy with coloring all the nets, etc. But in my experience, it's nice to have an overview if you have a board with a lot of complex designs and a lot of complex routing. You want to keep track of things and you want to have a visual insight into things. So I would say use as much blankets, 50 ohm designators, bank annotators as you possibly can, because then at a later stage, actually in the PCB design overview window, you can have a good look at, you get a good overview and you can select, deselect the signals that you want to view, and you can actually derive design rules from them, which is going to be handy later on. So for now, we're just going to zoom in a bit on these data groups. So there are four bytes of each of data groups. And if we look, well, if we represent those signals a bit closely, we can see that they're more or less point-to-point routed, and they look a bit like this. So they originate from the memory controller, in our case the SoC. Then we have some stuff on the PCB going on, so some VIA, some breakout routing, the main bulk routing, etc. And finally, the traces arrive at the DRAM. So far, pretty simple, right? I mean, we got just 32 signals going from point A to point B. We have to route them. What could go wrong? Well, the problem with DDR is that there are quite some constraints on them. And since we're focusing in this talk on timing constraints, let me show you a few of them. So we got some constraints here, more constraints, more constraints, more constraints. And there is not enough time to go to explain into detail, but yeah, you see where this is going. There's a lot of things to take care of if you want to have your layout functioning properly. And apparently, I see some stripes on the projector. There's something high speed going wrong there, but okay. So the first actual problem that we encounter is that all these delay requirements are actually given in the time domain, so in picoseconds. But what we want to know is actually how that corresponds to physical trace length, because we have to be matching signals on the board within a certain physical length. So we have to make the translation from the timing domain into the physical domain. You cannot see that over here. So we have to know if this 10 picoseconds will correspond on the board to, let's say, 1 millimeter of routing or to 50 millimeter, which would make our life very easy. There are actually 3 ways to get from timing to tracing. First one is to use some values from the datasheets or design guides. As you can see here, the manufacturer of our SoC says, okay, we have a skew constraint of 10 picoseconds over here, and that corresponds to a skew constraint of 58 mil on the PCB. I'm not too keen on using values like that, because the problem with something like this is that it's always based on some kind of reference stack-up that your manufacturer has in mind. And, well, in my experience, I've never used a reference stack-up that the manufacturer put inside the application note. So this whole skew constraint of 58 mil is, to me, it's not telling me anything. Second thing we can do is actually calculate the propagation delay. Well, you can do that many ways, but for instance, inner layer routing, so strip lines, there's a nice propagation delay formula where you have to know the velocity of light in vacuum, and you have to know the epsilon r or the dielectric constant actually of your PCB material. So you can do that for strip line. You can do that for microstrip as well. But luckily we live in 2019, so there are also a lot of good online free tools available that help you do that. So for instance, here there's the Saturn PCB Toolkit. It's a freeware tool, and you simply put in everything, your conductor properties, your substrate options, so you'll have epsilon R on the right. You give in what type of circuit you want to know your propagation delay from, and voila, there comes something out of it. But the third option, and to me the best option to get the propagation delay of your signal on your specific board that you're designing, is actually to ask your bareboard manufacturer. Because at this time in the design, there probably already has been some communication with the bareboard manufacturer, because you have come up with a stack up, you ask them if they have the right materials, etc., etc. And they probably also have done some calculation with 3D solvers on how to get your impedances right, etc. So they know their materials they're going to use, they know their process variations, so they're the ones that are going to give you the most accurate value for this propagation delay. So, as an example, we take the 10 picoseconds that we've seen before. We ask the manufacturer, or we have put in the formula, it doesn't really matter, and we can see that this 10 picoseconds of length matching requirements actually relates to a rule of 1.5 millimeter physically on the board. So, how do we actually measure total trace length in Altium? Well, that would be simple, you would say. You just go to the PCB inspector, put up the net list, select the signal that you want, it gets highlighted, and voila, there is something as, let's say, 23.5 millimeters. Okay, 23.5 millimeters, good. But what does that actually tell us? If we go back to the signal representation, what are we actually measuring? Well, in the case of Altium, we're actually measuring only this part of the signal. So, for instance, what about via? What kind of impact would actually changing layers have on your total signal length? Is it included? Okay. In that case, my bad. Apparently it's included, but still, there's a good point in actually knowing what. Yeah, did it used to be? Thanks. But still, the point I'm trying to make is that we can see how changing layers of a signal can actually impact the signal, and how much of a change it actually is. So if we have a signal that originates on layer 1, and we route it over layer 3, it's going to go down the via hole, and we end up with 10 millimeters of trace length on the top, 20 on layer 3. We got some space in between where the signal has to travel through the via, and we end up with a total signal length of 30.3 millimeters. So let's say we have the same signal, and we're going to route it over layer 8, all the way down the bottom, for whatever reason. So still, we have the same signal on the top. It's going to travel a bit longer through the via hole, and it is arriving on layer 8. So same 10 millimeters on the top, 20 millimeters on layer 8, but now actually it has to travel 1.1 millimeters inside the via barrel. So if we, this gives us a total length of 31.1 millimeter. So to summarize, changing layers. Layer 1 and layer 3, it gives us 30.3 millimeters. Routing the same signal over layer 8, it gives us 31.1 millimeter. The difference between that is actually 0.8 millimeter. You can see where I'm going here. As you can see, if we compare that with our timing requirement that we got earlier of 1.5 millimeter, that actually makes a difference. So we can use use this as our advantage. If we need to get a bit longer signal, but we don't have the trace length, we could think about moving it to another layer, if that's possible or not. I mean, there are a lot of other factors to think about, but it could be a possibility. So it could be an advantage and a disadvantage. So now we looked at the PCB, we looked at the vias, but what about actually the pin package lengths? So, for either the SoC and the DRAM, there's going to be the signal has to travel within the package. For instance, if we have a BGA package over here, in this case it has some bond wires, and there's going to be a difference between in length that the signals have to travel within the substrate of the package. And as you can later see, that's going to be a big influence on our board. So we have different propagation delays for different signals. So usually for DRAM devices, these flight times are actually included into the design rules. So the 10 picoseconds that we saw in our example usually takes into account all the flight time differences within the DRAM devices. However, if we look at a memory controller, in this time our SoC, and especially when you're using something with FPGA logic, then usually the flight times are not included in the design rules. So you have to take them into account when you're designing a board. So, how do we do that? We have the same signal as before. We're saying we found out that it actually travels 23.5 millimeters through the PCB, including the vias. But luckily, Altium has something what they call pin package length. And that's a field that we can use to put in the value that in millimeters or in mils that the signal has to travel within the BGA package. How do we do that? Well, we can pull up the component pin editor, and there is this pin package length value. It's something that it took me a long time to actually figure out that it was there. I always overlooked it, but it's there. So then the question is, this is still given in length, so in mils or in millimeters. How do we get there? So how do we get, again, how do we get these timing figures? Again, multiple options. In general, you could get them from the datasheet and sometimes from a special datasheet after you sign an NDA, because manufacturers are not always that keen to give them to you. In the case of FPGAs, it's actually depending on how you implement your FPGA blocks. So how you connect, in this case, your DDR logic. So you get that after running the synthesis tool. And you get a table that's looking something like this. It says I/O bank, the pin number, what type of connection it has, and it gives you a minimum trace delay and a maximum trace delay. Well, in Altium, there's only one value we can put in. And in most situations, it's fine to just average those two values and put that into the component pin adder field. Because that minimum trace delay and that maximum trace delay, that is taken into account all the process variations that the chip manufacturer has. So in average, it's gonna, averaging out is the best we can do, actually. And we end up with a table looking like this. So, next question, of course, we're still in the time domain here. So we're talking about picoseconds. So can we use the same formulas as we did before? So we got picoseconds here. could we use, for instance, the strip line formula that we did. If we would do that, we would get something like this. But can we? First thing that may strike some people is that we actually, if we use this formula, we end up with quite long signal lengths. So for instance, the top signal, 504, using this formula, it would tell us that the signal actually has to travel from BGA ball to the actual die, and that length is 15 millimeters. To me, that just seems a bit, how are you doing? That seems not possible, actually. So, technically speaking, this is not the correct way to do it. We should actually use the electric values, so the epsilon r, of our actually board. Yeah?
Does it really matter? Because it isn't just a relation from
Keep that question, please. Exactly. So, like I was saying, the epsilon r of the plastic mold of the package is not the same as the epsilon r of FR4. But, as a gentleman in the front here was saying, in practice, it's absolutely fine to use the same formula, because we're not talking about absolute timing values, so about absolute time that it takes a signal to travel from point A to point B, but we're talking about relative, because our timing constraints are relative to signals that are relative to another. So knowing the actual travel time that the signal has to travel through the board doesn't really matter. So in practice, we can absolutely use the same value formula to show the relative impact of the package flight times on the PCB layout and use those to set our design rules. But of course, you should be aware, we're no longer talking about absolute values here. So you can't tell anyone that your signal actually takes 15.17 millimeters of travel time inside the package, because that's not true. And we do this because usually we don't get any epsilon r values from the BGA manufacturers. It's just so we have to work with everything that's on hand. So for an example, if the difference between two signals inside the package is 10 picoseconds, then in this case we can compensate that difference on the PCB by adjusting the copper trace with 6.7 millimeters. So now we have all these values, and thing we can do now is to put them in the component pin editor. So, little sidestep here. What about so-called pin-compatible packages? If I have a look at an FPGA vendor here, some obviously will recognize that one. We can see on the bottom here that it's actually offering us, in the same package, it's offering us 3 devices. They have the same I/O, but there is other logic in between, so less building blocks. Well, in this case, pin compatible does not per se mean flight time compatible. Why is that? It could be that going from this device to this device, the physical die inside the package is arranged different, is bigger, is smaller, whatever. There are changes here. So what do we have to do? We have to analyze the difference between the packages. And that table is also very well readable with all the noise. So we got an average trace delay of the first package that we're using, and then at a later stage we would like to populate it with its bigger brother or its smaller sister or whatever, and we end up with some other trace delays. In this case, actually, the difference between those two is pretty significant. Because if we look at the same signal over here, in one package it is 61.6 picoseconds, And in the other one, the same signal actually has to travel as a delay of almost 93 picoseconds. So yeah, that difference, 31.2 picoseconds, is actually already bigger than our initial matching requirement that we had to take care of 10 picoseconds. So think about the impact that's going to have on the PCB layout. So second thing we have to do is actually adjusting the layout to facilitate both packages. But in this case, it seems that's no longer possible because the difference between two packages is 32 picoseconds, and we're only allowed to have a 10 picoseconds delay. Well, in the case of DDR memory, we can cheat a bit. Normally, I don't like cheating. In this case, I do. And we can do that by actually using a higher speed grade of your DRAM device. What that would mean is that if you look here we have let's say we have a memory component that is rated 1.3 gigabit. We're using our link at 1.3 gigabit, and that gives us the example of 10 picoseconds of timing constraint that we have been using throughout this presentation. But what actually happens is that if we would use a higher rated memory component, we are actually gaining a bit of timing margin here. And we can use that to our advantage if we still want to have one physical PCB layout that can support both or all four of the pin-compatible chips that there are. So actually, we gain, by doing this, we would gain 46 picoseconds of margin. And on the PCB layout, that actually means that we go from a length matching rule of 1.5 millimeter to a length matching rule of 8.4 millimeter. And that would make your life a lot easier. So back to the PCB. We have now put in all the values, and we can actually see that our total signal length, which is now including the packet flight times, has gone up from 23.5 millimeters to 30.1 millimeters. So up until now, we've been looking at relatively simple point-to-point signals, all the data groups. How do we deal in Altium Designer with what we call fly-by routing? So a group of signals originate on the SoC, and it goes to the first DDR chip, to the second chip, to the third, and so on. Because if we looked at our timing requirements that we saw earlier, there are actually usually constraints for each segment of the layout. So how would we do that? Again, if we look at another representation of the signal, as you can see, it's getting a bit more complicated than it was before. So no longer a straight point-to-point layout, but it's now originating from the memory controller and going to each DRAM device, and then it gets terminated at the end. And on the board, this actually looks like this. So we have a signal going from the SoC over to the first DRAM device, and then from the first DRAM device to the second DRAM device. Altium actually only shows us only the complete length of this signal. So in this case, the routed length is 50.3 millimeters. And what we actually would like to know is per segment trace length, because that way we can satisfy all our design rules and timing constraints we had before. So how do we do that? First, there's a good feature to know, and that's actually the xSignals. So we have to create an xSignal from the SoC over to DDR device 1. Secondly, we create a xSignal from the first DDR device to the second DDR device. And finally, we create an xSignal that's originating at the SoC and it's going to the second DDR device. And the good thing about this is that we actually, when we have the length tuning rules, we can create rules for each segment and for the total length. I'm almost finished, so if you, then I'll come back to you. So, like it's shown here, we can create length tuning rules for each individual segment. So, what do we end up with in the PCB? Now, instead of looking at the net inspector, we're looking at the xSignals. And when we select a specific net, you can see there's we can measure from the SoC over to the first DRAM device, from the first DRAM device over to the second, and actually we can measure the total length like we measured before. And we're actually now looking at a total representation, so including vias, including pin package length, and including all the routing of our signal. And that's what we want. So, questions? There was at least one here up front.
Just,
Can you, I have to give you the microphone because for the recording.
shouldn't there be a length match between the last die and the termination also?
Yes, you're correct.
Yeah. But as I remember, if you use the Altium wizard, it's not including that one.
No.
No.
No, indeed. There is, nowadays I had some backup slides, but there's nearly not enough time where I was going to show you how to do it with the Altium DDR wizard. And also you've seen from the presentation that in Altium 20 there's something with the layer stack manager that you actually can figure out the propagation delay there as well. But I've never got that working so far. So I'm always creating manual xSignals, and that's working best. But before there were xSignals, we would actually create a separate Excel sheet, fill in everything, and do that. And then you have a separate calculation sheet that's very hard to maintain, because if you change something in the layout, you have to change the Excel sheet. And the good thing about this is that it's actually a very reliable tool. Does that answer your question?
Yeah.
Good, thanks. Any more questions? Okay, well, thank you very much. And I hope you have a good day today. And thank you.